All right, so shall we begin? Hello,
Sounds good.
everyone, and welcome to this episode of Twitch TV, or Proteus TV on Twitch. Today, us three are all guests to the channel. We're collaborators of Professor Bongard and the others at UVM. We all come from Yale University, where we worked with Rebecca Kramer at the Faboratory. And today's topic will be shape-changing robots. But first, I'd like to introduce all three of us. So I am Dylan Shah. I just recently graduated from this lab. And
Hi, I'm Liana Tilton. I'll have a more elaborate introduction in a minute, but I'm an undergrad.
And I'm Stephanie Woodman. I'm currently a grad student with Rebecca.
yeah, so thanks everyone for tuning in. And if you have questions, please place them in the chat. And Liana will be monitoring this, and she'll bring up your questions if you have them. But otherwise, we can dive right into the presentation. So today's format will be a hybrid between some technical content about shape-changing robots, and then also a little bit of discussion about how all three of us came into this lab and where this experience has shaped our professional development, and also will point towards some of the open challenges in this field of shape-changing robots. So all of our projects through the last couple of years have been tied together by this shared interest of morphing robots.
Yeah, so I guess I'll introduce myself first. Like I said, hi, I'm Liana Tilton. I am a current sophomore undergraduate at WashU in St. Louis, but I'm originally from New Haven, Connecticut. So throughout high school, I worked with the Yale Faboratory, and I've worked there ever since through my summers, and I actually ended up taking a gap year, so I did my gap year as well. I wanted to give a quick shout out to First Robotics. I had to place their little logo there because that's really where I got my start in robotics through First Lego League and First Tech Challenge, and really getting that hands-on experience was super valuable. So anyone who is involved with that, or anyone who has a younger student or is younger themselves, I'd really encourage you to get involved with that. And then, yeah, as I mentioned, junior year, I started at the Faboratory working under Dylan, and then been working there for the past 4 or 5 years. And I decided this summer that it's time to take another step in my research journey. And I'll be out at the Charm Lab at Stanford working under Professor Allison Okamura, and taking what I've learned with soft robotics, the manufacturing and testing skills there, and applying it to a soft robotic wearable device, which is really where I hope my interests will take me. I'm really interested in more human applications of soft robotics, and specifically wearables. So definitely looking into grad school, maybe doing an industry internship, but options are open there.
Yes, so Stephanie.
Hi, I'm Stephanie. I am currently a second-year PhD student at Yale in the Faboratory with Rebecca. I came in and started working on a bunch of projects with Dylan, and now I'm starting to branch out on my own, but it was a really, really fun time working with both Dylan and Liana during my time there. For my undergrad, I went to Boston University, where I started as a biology major and realized that biology wasn't for me. I didn't want to go to med school, and switched to mechanical engineering starting in my sophomore year, and then had a really fun time with their rocket team and a bunch of other clubs and programs. That was really, really fun. So my ultimate goal as I'll tell you much more about in a second, in Rebecca's lab, is to develop adaptive robotic systems capable of onboard proprioception, external sensing and control, and then use these robots to further the human agenda, both in space and on Earth. So it's a really exciting time to be in the field of soft robotics, and I can't wait to share it with you guys.
Yeah, thank you for intro, Stephanie. I just want to read a few questions here. First one, I hope we got it answered eventually, but we are all from the same lab, the Yale Faboratory. That's where we all met. And then the second one, First Robotics sounds cool. When you get a moment, could you say a bit more about what it is? Yeah, so First Robotics is a national or perhaps international organization, and they host 3 different, maybe 4 different tiers of robotics competitions for elementary school all the way through high school teams. And I highly encourage you to check it out. It's a pretty big competition that a lot of people are into in high school.
Yeah,
Let me hope that answers your question.
when Liana joined the lab, we were very excited to have a young high school student who had already had robotics experience. So for students who are watching this, it's never too early or too late to start jumping into research if this is something you're interested in. So reach out to professors, you never know what'll happen. All right, so now the last person that needs to be introduced, I guess, is me. I'm Dylan, and I actually started my research experience way back in 2014, I guess, at Iowa State, where I applied novel sensing techniques to the end effector of a robot arm and put that robot arm on a mobile platform. We could go in between growth chambers where plants were grown under very controlled environments. So what this showed me is that by making some automated, repeatable robotic techniques, we could collect data on plants that otherwise would be very difficult, maybe even logistically impossible to collect on plants as they grow. And this is useful to agronomists and farmers for understanding how their different plant varieties could grow in different current environments or also different future environments as the climate and weather patterns change. But as I got toward the end of this experience there, I began to wonder how we could use new materials to make robots that maybe could interact more naturally with humans and with soft structures such as the plants and fruits that I was dealing with in my agricultural robotics experience. And this led me to Rebecca's lab, where I worked on soft robotics for a long time, I think just about 6 years, because PhD is a long journey. And I started out by wrapping around some robotic skins around soft things. When I say robotic skin, I mean we integrated actuators and sensors into a thin fabric that you can wrap around something and turn it into a robot. This first experience kind of got us as a lab, like this wasn't just me, I did this with many lab mates, it got us thinking about how we could add new functionality into surfaces and this is what this presentation today is mostly about, how could surfaces change their shape to change the functionality of whatever they were wrapped around. And this led us to start thinking about morphing robots, shape-changing robots. By the end, I kind of was looking for jobs and found some interesting companies within the field of soft robotics that settled on one, but I won't quite give away that secret until the end, and it will make sense at the end how I chose this current project. So yeah, that's a brief bio for all of us, and we'll loop back at the end to some discussion, but we figured before we dive into some deep technical stuff, we should introduce ourselves so you know who we are listening to and who we are asking questions to in the chat box. So our topic today is morphing robots. But before we can even think about what a morphing robot is, it's first important to look at what examples of locomotion we can already see in the world, because we can get a lot of inspiration and understand some general principles if we can observe something that already exists. So this is true for Bongard's group, our group, the soft robotics labs in London, Italy, South Korea. A lot of us in this field can gain some deep insight and inspiration by observing the natural world. And what we can see here is that there's many ways that animals move. The first of which we're very familiar with is legged locomotion, where you have some underlying bone structure that allows some rigid links of material, our bones, to move in precise and controlled manners. What I mean by this is, like, if you think of your finger, for example, it can bend about some specific joints, but you can't bend it like way towards your pinky. Your bone structure gives some guidance to the motion, and this in turn makes it a little bit easier to control in most situations and allows us to walk in an upright posture. And we just feel this is natural because evolution designed this locomotion gait and this body pattern to pair together very nicely, and we can locomote with legged locomotion all over the ground. But other animals can exhibit vastly different styles of locomotion, like the snake here. If we look at this, it's completely unintuitive how this thing is moving sideways, because we're so used to moving one foot in front of the other, stepping on the hard ground, but this snake somehow has really precisely adapted friction properties on its scales. And then as it wiggles, this special frictional surface allows it to slither in crazy directions across the sand. And then if we look even broader in the animal kingdom into underwater environments, you can see this dolphin just elegantly gliding through the water. And it's a completely different locomotion gait and style than what the other two are exhibiting. It's smooth, fluid. There's some play of friction, but also hydrodynamics are at play here, and that's a whole different beast than granular friction that the snake is leveraging. So then you could think about what types of behaviors would these animals exhibit if they were placed in a different environment that evolution hadn't designed them for. And a very funny example is when you see a dog jumping into the water, it tries to use its rigid bone structure and its legged locomotion patterns to swim in the water, and it's very inefficient. You can see this dog paddling like crazy, and he's just barely moving away from the golden retriever. So the dog's gait, just like our gait, is very environmentally adaptive. This dolphin that you see here got beached on the shore of this ocean or lake. Probably not lake because dolphins don't live in lakes, but this ocean. It had to be saved by a human because the gait that it had been designed for does not allow it to slither across sand anywhere near as well as the snake, doesn't allow it to walk anywhere near as well as the dog could. But then once it's placed back in its natural environment, its body structure, meaning this super fluid, continuously deforming dolphin body, and the fins can work together with sort of an undulatory gait and allow the dolphin to propel itself through the water again. You can see it's trying to flop on the sand, and flopping doesn't work on sand. So the takeaway that we can learn from this is that there's a tight interplay between the robot's body and what types of gaits and motions it can exhibit in the world in order to operate effectively in a specific environment. And we see the same principle and the same feature and limitation, however you want to look at it, at play in our man-made robotic world, where this, for example, this Boston Dynamics robot exhibits legged locomotion, and it can prance across the ground and exhibit some pretty strong force on this door and open it. But this thing would be terrible at swimming for the same, not the same, but very similar reasons as why the dog was not very effective at swimming. But we can change the robot's body structure and use a different style of gait to make effective locomotion underwater, as you can see with this little flipper robot. But again, this flipper robot would not be nearly as good at walking on land as the Boston Dynamics robot was. Its body dictated what types of gaits it could exhibit, and then those gaits are limited in their functionality based on what environment they're operating in. And finally, for a completely different take on locomotion, humans can use wheels on our man-made machines. Like you can see this dog riding around on the Roomba. So in our lab, as we were looking at these very different styles of bodies for these mobile agents, began to think about, would it be possible to actually make a robot that changed its shape, changed its body in order to change its function? And as a result, maybe we could make robots that could adapt their locomotion to be effective in different environments. This concept is shown here, where you could have a little rolling round ball robot, like a Droideka from Star Wars, and then the thing would kind of deploy out, squish itself, and make a snake-like body and slither through some rocks. And then if it got to some hot sand that were causing some problems, maybe it could extrude some limbs and start crawling over this new terrain. So in effect, the idea would be maybe you could have n different body plans that could operate over m different environments and allow the robot to not ever reach an environment or obstacle that it could not overcome. Because if it couldn't do it in one form, it can shapeshift into another. Another way to think about this, for those of you who have seen Robin Williams films, the flubber from this Disney's Flubber movie is the ideal physics-breaking, shape-changing soft robot that can just do anything at once because it can change into this dancing form. It can be a blob and just hide in the background. It can bounce around. So yeah, we can see many different inspirations for how the form of robot could affect its function. We looked at the existing state of the art. You can see this kind of summary graphic here, where there have been a handful, maybe a dozen or so robots that distinctly change their shape to change their function. And I'll highlight a couple of them here. If you're curious, you can look at our lab's website, which we will post a link. Liana, could you post a link in the chat right now for the Faboratory website? Because I don't think we have that in our slide. Yeah, you can check our publications page, and there's a shape-changing robots review that will show a lot of these robots in action. But in the top left, we can see that this robot changed its shape to roll over this rock, kind of rolled up, and it was in this log-like shape, and then it sucked up part of its body to make it so that robot could roll over the rock rather than having to find another path. This is a simple, super simplified toy example, just exploring the feasibility of the basic concept. But you could imagine in some cluttered forest or a rocky shoreline, there might be situations where rather than trying to navigate around a series of obstacles, it'd be useful to just shape change and go over them or around with a simple pattern rather than a complicated path. So Liana will be talking about items A and B, so I won't go too in depth into these actually. But there was other research from Barry Trimmer's group. I think he's at Tufts at the time. Could be wrong on that. But this caterpillar robot in the top right started out being able to do an interim gait across this surface. And then when it was startled, it could curl into a ball and roll away super quickly. So by changing from a flat to a round shape, this robot could exhibit two dramatically different gaits and increase or decrease its speed with the trade-off of the faster rolling gait costed, in this case, a lot of energy. So it was a trade-off. It wasn't always best to exhibit one shape and one gait, but there was times when it was better to shift to a different shape and use this faster, more expensive gait. Yeah, and I guess the final example I'll highlight today is this 1D, where with a simple single degree of shape change, simply changing the diameter of this wheel, engineers figured out how the robot could switch between a relatively fast rolling gait that could roll over steps and over obstacles with the wide diameter wheel, but then it could collapse down into a shorter form and go underneath overhangs and obstacles. So a single degree of shape change is sometimes all a robot needs to dramatically change its functionality and adapt to whatever problem it was facing at the time. So throughout this presentation, each of us will share a couple projects that we have conducted at Rebecca's lab, the Faboratory, under this theme of trying to make highly adaptable and flexible robots. So with that, I think there's the citation at the bottom for the review. With that, we'll dive into our first set of projects, which will be presented by Liana. So Liana, take the floor.
Yeah, so zooming in on figure A of Dylan's past slide. And this was the very first project that we did exploring this idea of shape change. We like to call this the Morphing Robotic Skins project. Oh, I guess if someone could go ahead and play that That would be great. Hopefully it plays on loop. If not, we can just keep replaying it. But essentially what you're looking at here is there's this cylinder, and it's actually a cylinder of clay. And wrapped around the cylinder of clay are two what we call robotic skins. So the first one, which you cannot see, is what is being inflated, and you see those little bubbles coming up, and that's our pneumatically actuated robotic skin, and it allows this cylinder to roll. And then the second robotic skin that you can see is this white fabric that's spandex, and it has hand sewn cables into it. And what we see here is that if we pull certain cables, we're able to achieve shape change of this entire robot via the shape change or via the sculpting of the clay underneath. I just mentioned sculpting, and we did take a lot of inspiration from artists and sculptors, and we even brought in a sculptor to the lab to examine how applying different forces in different places can get different shape changes of the body underneath. So this was our very first step, proof of concept, to show that if you change the body shape of a robot using this very simple robotic skin, we're able to achieve a task where here it's achieving the task of rolling over this rock. And so this was very insightful and confirmed that, this idea could work. But reflecting on this particular project, there were a few things that made it a little difficult. And one of them was working with clay is just very messy. So if you want to go to the next slide, this was our second step in the project. It's a similar idea, but instead of the clay, it's now replaced with an air body. So it's just another pneumatic bladder that is able to be blown up or have a vacuum be pulled on it and flatten. And we like to call this pancake bot because when we pull the vacuum and it flattens, it looks like a pancake. So what we see here is that when the body inside is inflated and it's in a cylinder shape, we're able to use those same pneumatic actuators that you saw inflating on the previous slide to roll the cylinder and have a rolling robot. And then if we pull the vacuum, you'll see this more in the video. We actually shout out to UVM. This is some simulation work that was also done for this project from you guys. But if we pull the vacuum and get in the flattened state, those same exact pneumatic actuators are able to actuate and have inchworm locomotion. So here we go. Let's look at the video. The body inflates and the body shape changes from flat to a cylinder. And then we inflate the pneumatic actuators on the outside to get a rolling locomotion. And this is ideal for a flat ground because rolling is a lot quicker than inching on the flat ground. But then it faces an incline and it wasn't able to roll up this incline. So instead of trying to roll and fail, it will pull the vacuum, flatten, and you will see it inch. We also tested this on some other surfaces. So on the bottom left, you see those granular surfaces, just some rocks and sand. Based on intuition, you can probably assume, you probably would know that trying to inch in sand is not very efficient and there's lots of slip. But if you inflate the robot to its second state, which is the cylinder state, it's able to roll quite efficiently over that same sand surface. So this was our next step, and it was really exciting to see that it's literally the same exact robot, it's just changing its shape, and it's able to do so many more things by changing its shape. I think you're muted, Dylan.
I'd like to make a brief interlude before we move on to Steph's projects and make a few observations of the two robots Liana just presented. The first observation is that all of these robots had a surface, and as the robot changed shape, this surface was stretching and deforming in order to accommodate the new geometries. This is a fundamental property from differential geometry that can be proven to be true for all surfaces that are changing shape. As they move and bend, parts of their surface must stretch. And this is especially true in the real practical world with soft things, because as the morphing robot with the robotic skins question in the chat. So we'll go back a little bit and address this. The fluid in this, I think, was just a very simple friction model. It did not account for like turbulent dynamics or anything. It was just a like 1/2 drag coefficient times velocity squared type of a friction function. And I think this is common in the evolutionary robotics community, just because when you're doing many simulations with a high number of voxels going through water, it can, at least with the technology available when we wrote the paper, maybe it's different now with parallel computing and everything. It was tough to simulate more higher order dynamics. So we just went with the basic quadratic. Yeah, so as these robots are moving and bending, they will be stretching. And you can see this in our everyday life by watching people's tattoos move as they bend and flex their muscles. They have the same volume of muscle under here. So it's not like material was being added to inflate their arm or something, but just the shape of how that volume was configured is changing, and it affects all parts of the surface differently. Finally, we can note that all of the electronics for both robots Liana presented, the morphing skins and the pancake bot, both of them had their electronics off board. And this is a fundamental limitation of having rigid electronics on board the robot is kind of incompatible with this basic problem of the surfaces need to stretch with the robot. But they all require the electronics. They're very useful. So within this whole broad arc theme of trying to make shape-changing robots, we started to realize that it would be useful to be able to make easily scalable and integratable stretchable electronics. So I laid some of the groundwork with a couple of my lab mates, and they were even working before I was around, so I can't take all the credit for this. There's this field of stretchable electronics, and a lot of them are based upon these liquid metal alloys that are, in this case, it was gallium and indium mixed together at a special eutectic concentration. So it's liquid at room temperature. That's the practical result of this composition. And we mixed in some oxides with a special manufacturing process that allowed us to get a like kind of toothpaste consistency like paste that we can spread over stretchable surfaces like silicone or stretchable VHB tape. And if we pattern them with some laser cut masks, we can then make circuits with this. And what you saw in this video was at first just a trace of this paste being stretched on silicone. And then at the second half, we actually put a resistor on top. And you can see that because we have this nice paste-like consistency, the conductive liquid metal sticks pretty well to this resistor, even as it's stretched. It's not a perfect system. There are limitations like how far you can stretch it and what types of shear and undesired forces it can withstand. So it's not perfect, but it is a starting point that allowed us to make some interesting stretchable circuits in this journey. One practical circuit, that we made allowed us to put sensing electronics, which you can see here, the stretchable circuit board here, put some sensing electronics right on the surface of the user and have it interface with the stretch sensor, this gray thing in the background. And together, the two can detect how far the user's arm was bending. Now, in this case, we intentionally put the electronics in the most stretching part of the user's elbow to show that by introducing stretchable electronics, you don't have to think as much about where you're going to place the electronics. You can integrate it tightly into your system, in this case, sensing sleeve. And it kind of pushes us towards the ability to integrate our control electronics into the surface of our soft robots. So you could imagine putting sensors and little actuators that can apply the tension to the cables in Liana's morphing skins. If you had some sort of stretchable circuit that you could embed in there along with those strings and the pneumatic ladders. This is where we're going with this work. And this finally can help me answer the question of where I'm going now that I graduated. I'm learning how to apply these similar types of materials, these liquid metals and silicones, to kind of a surprising application area, which is, well, the first one I already talked about, which was applying stretchable circuits to the surface of humans. In other words, using stretchable electronics to make interesting wearable devices. The second application that we're working on here at RECA in Pittsburgh is applying liquid metals and stretchable silicones actually to the semiconductor industry. We have a question in the chat box. Did you or do you plan to do any acceptance testing to see whether people might want to wear smart garments? The short answer in the limited time of this particular study is no, I did not do this. But there's a whole body of literature around this, of even doing some clinical trials of kind of assistive garments, ranging all the way from the exosuit industry, which is mostly focused on actuators. So like integrating cables onto users' elbows and hands. Primarily, most of the studies I've seen were looking at people with mobility impairments. So like arthritic patients or people with carpal tunnel syndrome, these types of things, or even tremor patients are the current most eager kind of adopters of this type of technology. But there's a second level of user that's maybe a little more common. You might see more people that are interested in kind of the smart health industry with like the Apple Watches. This type of a customer, the thought in kind of the startup space and the research space is that there will be some applications where the wearable stretch garment will be more easily to adopt than the watch. Now, it remains to be seen how true this assumption and this thought is as the field develops, but that's the hope, that we can meet those two kind of separate needs with this suite of technologies. Yeah, so the second application area that RECA was looking at is completely surprising to most of us in the soft robotics field, but these materials turn out to also be very thermally conductive, and it can allow us to deal with the heat generated by computer chips a little bit more effectively than the existing solutions. So if you're interested in that application, I encourage you to check out the RECA website, but otherwise we'll move straight to the next step with looking at how Steph has been approaching the whole problem of shape-changing robots.
So I'm just going to share with you a couple of my projects. First and foremost, I just want to reiterate my goal of, during my PhD, possibly during my career, just working towards these adaptive robotic systems that have, proprioception, external sensing, and control all on board. So Dylan did a really nice introduction of stretchable electronics. So I'll talk a little bit about my work on stretchable Arduinos. So that's embedding control. And then I'll talk a little bit more about both Dylan and my work, primarily Dylan's work on shape sensing sheets. And then another kind of technology that relates to the different modes of shape change, which I'll explain in a minute too, reversible adhesives. And then eventually get into another mode of shape change, which is subtractive shape change, which we're working on with the University of Vermont. So here, let me click, oops. There we go. So first, embedding control. So Dylan introduced this paper by Shan in our lab and Dylan that was published in Advanced Materials. Called about Nature. Oh, it says advanced, which that's a typo. Not embarrassing. It's Nature. Okay. So we developed this biphasic gallium indium alloy that you can use to connect different circuit components. And so we wanted, once we developed this technology, we want to make it more complicated, more useful to the space. So I'm working on developing stretchable Arduinos. So kind of I call it the commercial circuit transfer process. So you take the circuit design from the Arduino website. They have it in AutoCAD Eagle files, and then we adapt it for our circuit making process. So which includes making, the vertical interconnects smaller, separating traces kind of where we can, adding ground lines. And then we paste this design onto a substrate called VHB, which is a really stretchable tape, put masks onto it and paint our circuit design onto the mask and peel off the mask, and then you have your circuit traces. As a very brief overview, but here's the top layer where we have all of our circuit components. You can see the microprocessor, here's the big reset button, a bunch of capacitors, and the oscillator. On the bottom layer, you can see it's just traces. So those are just like essentially wire lead traces that need to connect things on the top layer. And you can also see how thin and flexible these circuits are that I'm developing. So this is a brief video of them working. So I've just plugged it into my computer. So you can see it booting up, starting to, and now it's remembered the program that I've already programmed it once, so then it's remembering. Excuse me. And then I eventually stop it and I reprogram it. And you can see it transferring, it's remembering, and then re-uploading the same program. So this is a really exciting first step. This work is not published yet. I'm really excited to get it to that point, but developing these complicated control circuits and being able to just kind of put them on soft robots or on wearables enables this kind of step towards untethered robots. So getting control directly on board and making use of this previously non-functional body space in soft robots. So next, I'll talk about embedding sensing and proprioception with Dylan on his stretchable shape sensing sheets project that we've been working on together. So it's this really neat idea where there are, you can see a bunch of the same node over and over. There are 6 of them arranged on this little strip. So it's the same or very similar circuit manufacturing process that I just described, but there are lines of both BNO, global orientation sensors, and strain sensors. So the global orientation sensors are able to give the exact position of where that sensor is. And then if you stretch it, which we don't do in this video, but if you stretch it, then the strain sensors and the strain rosettes can sense the relative change in position and change the surface estimation. So with this kind of technology, we look for, you can kind of paste it onto the outside of any surface or soft robot and get the real-time shape of that surface, which is really important for proprioception and eventually the ability to close the loop on shape change in soft robots to be able to get this adaptive behavior.
Just for clarity, could you explain to the audience what close the loop on shape change means?
Yeah, so if you start off as, let's just say a flat shape, and you want to get to a circular shape, your robot does not know exactly when it's gotten into that shape if it doesn't have closed loop control. So it needs to know that it's actually achieved the shape that it needs to achieve to complete that task. So if it knows its shape, then it can accurately judge whether it's adapted correctly. So kind of towards this enabling adaptability, Billy in my lab came up with this really neat idea for reversible adhesives that we worked on together, which can enable you to remove a part of a robot. So there's, I kind of think of it right now, at least as 3 kind of modes of shape change. You can have one ball of material and it moves and the matter stays. You can have a ball of material that you add to. You can add material to change shape. And you can have a ball of material that you remove material from to change shape. So it's kind of, you maintain your surface, your amount of material to change shape. You can add material or you can subtract it. So kind of towards this idea of modularity as shape change, reversible adhesives are a really neat idea just to add function to this. So it's the reversible adhesive here in this picture is the blue part, it's an SIS silicone adhesive foam. And so you can attach, when it's cooled, you put it, when it's hot, sorry, you put it together. Okay, never mind. Let me pause this. I don't want you to be distracted. So this, you have, it comes from inspiration from biology. So, you know, geckos can self-amputate if they're in danger, or if they can't escape from something, then they get rid of their tail and they're able to resume their functionality. On the other hand, ants are able to form a bridge only with many of them together to complete a task. So either removing or adding, and you gain a lot of functionality. So this adhesive, when it's hot, the SIS will melt, and then you can separate two pieces that have been joined. But if it's hot and you put it together and the SIS binds with the SIS on the other piece of foam, then it'll cool as one piece and then not be able to be separated. So in this demo, I like this one a lot. You can see our quintessential quadruped robot walking along, you know, in a terrain of unknown dangers, and a rock falls on it. And what does it do? It can't move. It tries for a second and eventually gives up. And what it can do is heat up using Joule heating, this reversible adhesive. And then it'll start, once it's hot and they're no longer connected, you can start to crawl away, and it can resume its normal gait and functionality without this leg, because it was able to overcome this obstacle using the reversible adhesive. So I think that's a really nice example of where shape change can save a robot out in the field from dying. So next up, I'll talk about another kind of on the spectrum of enabling adaptability, subtractive shape change. This is some work that Liana worked on as well, but that we're collaborating with University of Vermont to make these different structures. So they use, just say you have a block of material, like as indicated in this initial body plan. Our idea is that we want to remove some of these pieces of material to get the robot to be able to move forwards. And then once it's done that, we want to remove more material from that to get it to move in the reverse direction. And this is just how we're beginning to explore the idea of subtractive shape change. But of course, this is like an insanely huge design space. So a Bongart's group at UVM uses evolutionary algorithms to search this space and see which removal of voxels for the forward direction and then for the reverse direction, again, they are optimized for moving in either that forward or reverse direction. So then we go ahead in our lab and try to create this in reality. So with this is just a picture of the robot kind of mid-fabrication. And then the red voxels are the ones that are expanding and the blue voxels are inert and don't get any air. And you can see that it takes rather slowly, but it takes steps in the reverse direction as planned by these simulations. So this is just some very preliminary work on this topic, but it's another really exciting option for exploring shape change. And that is all of my projects. So Liana is going to go ahead and talk about another really exciting one related to outreach.
Yeah, so thanks, Steph. As you've seen, we've done some really exciting work on shape-changing robots. We have some really cool projects, and we've had the opportunity to share these, via publications and conferences with the soft robotics and robotics community. But we really eventually want to share this with everyone and have it be accessible to the wider community. So something that I worked on this summer was setting up our very own Twitch channel. You may have seen me commenting from it throughout this presentation, but it's called Twitch Plays Soft Robotics. projects, definitely a work in progress. But here's just a screenshot from the channel. Essentially, we have a webcam that's over top of one of our soft robots, and you're able to control its movements using chat controls. So if you type forward, it will go forward, and then left, right, and different controls via the chat box. And really hoping to eventually be able to share this with everyone, and you can go in and walk a robot yourself and see how soft robotics move. So be on the lookout for that. You can scan the QR code right there to keep up with our Faboratory Twitter, where hopefully we'll be able to post about this channel eventually. So yeah, I guess that is the final conclusion of all of our projects. Next slide. Yeah. Dylan, if you want to wrap it up.
So maybe, see if I click stop share, is it going to mess up with Twitch or not? I'll try it. Stop share. Yeah, so we've got a few minutes left. Maybe we could discuss a couple things that I think are open questions in the field, which we didn't really address in the main presentation. So I'll ask a couple and see if either of you could provide comments on this, since you're still working in this area. First question that came to my mind was, so if you have these shape-changing robots and you're trying to design some circuits, what types of things would you even want to integrate into them? Like what actuators, what sensing do these things need? And how do you think that you can integrate these without making some super bulky mess?
As expected, that's a very complicated question. I'm really excited about integrating, like kind of getting this intersection between soft and rigid robots. And one way we've tried to tackle it in our lab is through variable stiffness. So we've worked on a project called Variable Stiffness Robotic Skins, which is essentially like the OmniSkins project that Liana explained with the clay, where you can vary stiffness that way. And I think that's actually a really elegant solution to, you know, instead of coating some surface in actuators, if you need it to act as a rigid substrate, if the whole thing has variable stiffness, and you can say, hey, like switch it to be rigid, and it's rigid, then you can like drastically reduce the number of actuators you would need to create an entirely rigid surface in the first place. So I think that's a really elegant way to introduce strength into our soft robots and create hybrid systems.
Yeah,
Go ahead. Are you attempting to reduce the complexity of the problem by adding this constraint, or what's the idea?
Well, let's see, like if you have, that's a complicated question. What, can you say it again?
I was just trying to spit back at you your answer. What I heard was you want to reduce the complexity of the shape-changing problem by allowing different parts of the robot to switch to become more like a bone. So allow the robot to flip between being dolphin-like and dog-like in super simple terms.
Yeah. Yeah. That's the goal.
Yeah, I was just gonna answer that question. I think there's a challenge in working with pneumatics. Everything I've worked on is pneumatic system, and knowing the pressure limits based off of whatever material you're building your pneumatic actuators out of. We've had a lot of popping. So either detecting that via how much the actuator is stretching. So you're already doing work on the stretchable sheets, or I guess just placing some kind of sensor to detect air pressure. That's definitely a challenge that comes along with many of these robots that we've done.
Yeah, towards that end, I mean, like looking at different actuator types as a whole, like as opposed to having pneumatic actuators, I think electrically stimulated actuators are going to be really essential to integrate into these robots to get them to be more likely to be untethered without all that bulk and weight.
Right.
So do you think it will be easier to adopt existing pressure sensors, to use that example? Or have you seen novel, flexible, stretchable pressure sensors that could be adapted for this case?
I think there's been a bunch of work on like soft and flexible pressure sensors of all types that could be more seamlessly integrated than like today's current pretty rigid pressure sensors.
Okay, and so say we can get these integrated novel actuators or the pressure sensors to help us with the pneumatic application. So you can get the actuators. What types of environmental sensing do you think would be easiest to integrate into one of these systems? Because the autonomous car field, they have these relatively large LiDAR scanners, which I don't think we can see a flexible LiDAR scanner being introduced anytime soon. So to simplify the question, what types of sensing do you think will be easiest to implement in the field going forward?
I mean, strain sensing is obviously really prevalent in our field right now. So I think as far as ease, I think that's going to be one of the easiest ones, using like liquid metal capacitive sensors or other types of resistive sensors. But as far as true like external sensing, that's a really tough question. I can imagine some kinds of chemical sensors, maybe really tiny, like on a PCB, light sensors or touch sensors. But as far as like if we think of cameras, that's going to be a really difficult thing to
soft camera.
Yeah.
There's an interesting idea. I don't think anyone's proposed this at all, but so you might have heard of the Bratenberg vehicles, where you have like a little disc-like robot that can basically only change the speed of motors on different sides of its body. And it's got a light sensor. It changes the speed of those motors. I wonder if you can integrate these light sensors, you could make another variable in there of how the robot's shape can change based on environmental stimulus, in this case, super simple case, light. So a bird shape-changing robot that will not only change its motor speed, but also maybe its body shape in response to this light source.
Yeah. Yeah, I mean, that's a really neat idea. There's a cool paper out by Carell and Daniela Roos that kind of used, it wasn't shape change, but used this concept of, if one side of a circle sensed that it was darkness, it had just gone from light to dark, or the other way, just gone from dark to light, it knew which pneumatic bladder to inflate to then keep the cylinder in a kind of rolling gait. So I think that's a really, really neat way to interact with the world in like a very, binary light, not light sense.
That'd be really cool to implement into some of the earlier projects that I was working on. Yeah.
You can also picture, if you have many of these robot agents working together, if you have one scoot next to each other and then the light sensor becomes dark, that they're close to each other, and maybe you can get some kind of multi-agent behavior from just that very simple environmental sensing.
And for your reversible heater project, you looked into how you could make the reversibility part of that also embedded into the surface of these things to maybe make some sort of untethered version of that reversible guy.
I honestly haven't thought about it yet, but yeah, I can kind of see, I mean, if you have your quadruped that was just walking around along, and it had light sensors on top of the leg and the body. And then one gets covered, then, you know, maybe something bad has happened to it, and it could trigger the heating up of those of the reversible adhesive so that it can walk away and like gain its functionality. So in that would make sense as well.
Are there examples? So you presented the example of the chameleon that detached its tail in presence of danger. Are there not robots? Are there animals that add to their own body in any situations? Like, is there such thing as a reconfigurable animal
Oh gosh.
outside of the lab of
Outside,
Mike Levin?
yeah, yeah, it's fair. Outside of like the ants coming together in kind of this like swarmish behavior.
It's a
No,
multi-agent.
I'm
yeah,
not sure about modular, but going along with that, we've definitely, I know us three have discussed growing limbs.
that's true.
I'm blanking on the animal that was that, like a squid or something.
What about frogs, tadpoles,
Yes.
change?
Oh, yes.
Yeah, but that's kind of, I don't know, that's part of like the growing process. There's like
Right.
a maturing process, but that's still kind of a neat way to think about shape change.
So I noticed towards the end of your presentation, Steph, you seem to be more focusing on additive or subtractive shape change, whereas Liana focused more on constant volume shape change. Was that an intentional shift, or do either of you think one of the approaches is superior, or could you comment on those, both of you?
I might be I don't think any one of them is superior. I think one of them is maybe more achievable right now, maybe the constant volume approach, because, you know, there's a logistic problem of if you have many of these agents like these voxels, how do they locomote independently? How do they have independent control? How do they communicate with one another? How do they, once they know what they want to do, how do they crawl on top of each other and form these new shapes? So there's like the autonomy question of it, like beyond, like in theory, the best form of shape change I would say is additive or subtractive, where you can change matter, because theoretically you can put together anything. But then there's the logistics of how, and anything that's constant volume right now and shifting what you already have is, I think, much more feasible in our, at least in our current research stages, than something that has to come together and tackle all these elements of like real world physics and crawling over each other to create new shapes.
Yeah, I would definitely second that. I think Steph is just taking it an extra step further with additive and subtractive.
Excellent answer. And I was just taking a look at the time. We should probably wrap up soon here. I think it's
Any more questions from people? I don't see
yeah,
any.
Any more questions from the chat? Comments from either of you? Streams, wishes, concerns?
Don't think so.
No.
Well, it was very nice hosting the session with both of you, Steph and Liana. Thanks
Thank
everyone in
you.
the audience and in the YouTube channel afterwards for watching and supporting. And feel free to reach out to any of us via LinkedIn or email, or more on the internet. Find us. You can
Yes.
contact us if you have questions.
Nice. Thank you all.
All right. Thank you.
Bye.